Okay, so yesterday we were talking about transformations. Okay, so you can imagine us having a line. Oops, that's rather big line. So you imagine having axes like that. I still don't like that, still too big. Okay, and then you see that here we have a positive slope. It has a intercept of 6 up here. Goes something like this. Okay, that's our original line. And yesterday we were talking about transformations, doing a little bit of changes, and seeing what happens to the whole thing. In this case, when we do the first one over here, when we add 2 to this function, it moves it over. But you got to be specific on the direction. In this case, we learned that it moves it up to 8, maintaining the same slope like that. Then we learned that, okay, we've been doing this one. When we multiply it by 2, that one changes the steepness. Then, let's see, it'll look something like that. Hold on. I think I messed up because the y-intercept also changes in this example, right? Because if algebraically we could think about this like 2 times this whole thing, you can see that not only does it get steeper, it also gets a different y-intercept, so it's going to be like way up here, 12, and then it'll look something like that. Okay, those were the ideas. For this one, it's a little weird. We think plus over here, we think it moves right, but actually it moves left 2 spaces, maintaining the same slope. Let's try to draw that. Something like this, okay, would be green. And then if you're multiplying just x, well, that one is the one that gets it steeper. Okay, y-intercept doesn't change. So something like this. Okay. I realize it's kind of messy. So that was transformations. Okay, yesterday we talked about these things, and we'll just summarize this idea. Again, this stuff is optional. You won't be tested on this like if I am giving out a final, but it's just some cool ideas you'll see throughout your math classes in Algebra 2, later in pre-calculus, and if you choose to take calculus, you'll see these ideas again. Another way to approach functions. So now, there's some summaries. If you did yesterday's classwork, if you go back to the one with a bunch of tables, those 4 things on there, you would have summarized and thought about the patterns for each of these. So for here, you'll see that linear and quadratics often perform, like when you perform a transformation, in this case adding some constant k, that the same kind of change happens, right? The growth doesn't change for either of these, and then it moves up and down. This one, I think, is the simplest case. And then exponentials even work the same way. When you have some kind of graph like this, when you add k to it, then it goes up if k is positive like that. And then if I were better at drawing, the curve would look also the same. That's the first transformation. But you can also add k this way. Notice it's inside the parentheses, modifying k. This is where it behaves a little differently. It moves left and right somehow. But more specifically, when you went through those problems, if you graph them in Desmos, it's the x-intercepts that move left or right by k. So we have this opposite idea that happens, and yesterday we kind of previewed the inverse that's happening so that it moves left and right. The growth stays the same, initial value changes because it moves. You'll see that's the same for the quadratic. And then for the exponential, its initial value changes, stays the same, but then its growth changes. So it gets steeper or it gets flatter. the other one we learned. Multiplying by a constant k. Here are the changes for that. Lots of things change. The x-intercept stays the same. Quadratics behave in the same way. So let's create a short example. Let's say you had this one, right? A parabola. That's like x squared. And then we transformed it, y equals 2x squared. So we think, okay, the initial value changes, probably moves up a little bit. Its growth changes, it gets initial value, x-intercept stays the same. Yeah, in this case, like it just stays right here, and then it goes steeper, right? So it grows, your parabola grows a bit faster. Think about like this part like an exponential. So it gets to where it needs to go faster. For quadratics, it becomes narrower versus wider like this. So that's what this kind of transformation does, multiplication by k. These ideas, it's useful to know. You'll see it in geometry class when you take it next year, or maybe you've seen it already. For exponentials, when you multiply it by a negative number, it flips it across the x-axis. So if you had something like this, and your k was negative, it would flip it over to look something like that. And I've previewed this a lot in my do nows when I have similar functions. You've seen this before. And this one, it's the one that's a little weird. K is now inside modifying x. Each of these, now it's linear and exponential that are the same, where the y-intercept or the initial value stays the same, but the growth is the one that increases by a factor of k. Over here, the quadratic, it has some fancy relationship. The growth rate's a factor of k squared, and the initial value stays the same. And you can go back to yesterday's, or bring up Desmos, plug in a function, and kind of modify it and see these things do end up being true. Before we go on to the new idea, again, this stuff is going to be useful when we go back to Chapter 8, formally next week, to talk about quadratics, how to graph them, how to solve word problems with them. This idea of transformations will help you understand vertex form and how you move parabolas around in a graph. The vertex form is just a bunch of transformations that occur. You shift it up, shift it down, make it wider, rewrite it in certain ways. That's how you get vertex form. Okay, now on to the new idea. So today's main focus is inversing a function. How do you find the opposite function or the recycling function, as you'll see in some of our classwork for these given things? And you've done this throughout the year with solving, but now we're just going to write it a different way. So our first problem, okay, if you want to look at this slide given to you, you can work through it. I'm going to talk about them and write it onto here, one thing at a time.
Yeah.
So, as I'm reading, here we have a function machine, okay?
Yeah.
A blast from the past. Looks like when we put in a 3 inside, right, into this function machine represented by f of x, then it spits out 13. Okay, and then you'll notice over here, when I put in a 4, a 16 comes out. When I put in -3, -5 comes out. So explain in words and with an algebraic equation what this machine is doing for any number x that is put into it. Well, let's think. 13, 6. It could be growing linearly. I think this one does. So I'm noticing the change between here and here, 13 and 16. It's like a +3 pattern, 3 to 4. If you go back 6 from 3, that goes back 18. Yeah, so this seems like an equation for a line. So we can piece this together. Our f of x is something like growing up by 3. And then we got to figure out its y-intercept. So when I put in 0, what happens? If you want to write this out in terms of a little table for x and y's,
you want that on
or x
as well, right?
and f of x, right? We got -5, -4, -3, -2, -1, 0, okay, skip a couple, and then 3 and 4. So 16, 13. You imagine undoing this pattern a bunch of times. Now we go backwards, -3, -3, -3, 10, 1. Looks like I got 4, if I did my subtraction all correct. Okay. So far so good for part 8. So again, in the function machine, our input here is x. We put in that number, and then it does this equation and multiplies it by 3 and then adds 4, and then we get our output, f of x. So when we put in 3, 3 times 3 is 9, plus 4 is 13. When we put in 4, right, 4 times 3 is 12, plus 4 is 16. Right, that's the old stuff. And then we're on to part B. So Functions from America, it's this function generating company. They're trying to open a recycling department, which you would like to apply for. In this department, the outputs are put into inverse function machines. Okay, that's the new part. In this department, outputs are put into inverse function machine. We have some new notation. The inverse function, written f to the power of -1 of x, okay? F inverse, that's how you'd read this symbol, undoes an output and recreates the original input so that it can be recycled and used again. So if you put in 13 into the inverse function machine below at the right, what number should come out? And then what kind of, what would have to come out if the input is 16? What has to be put in? And then what happens if a -5 is put in? Well, imagine over here going in reverse. So the picture, it got cut off, it's like over here, right? Notice this picture down here and this one, instead of going forward as we've been doing, inverse goes the other way. So the inputs and the outputs got switched. The first part, when 13 is put into f of -1 x, right? So the inverse machine, it outputs, as we look in our table, 13, it was our old output, but now it's our new input. It's going to spit out 13, or 3, my bad, 3. For 16, it spits out 4. For -5, it spits out, well then, did I get it wrong? No, yeah, it spits out -3. So that was this last point over here. When -3 is put in, -5 comes out. Well, in this inverse, when we put in -5, we get an output of -3. Okay, idea-wise, it's not so bad. So far, so good. This inverse idea, it has a table or a new notation, some new symbols for you. Yeah. Okay.
What? Say again?
So here's part C, right? He needs to demonstrate that he understands the inverse function process, explains in words the steps to inverse a function, and how do you undo it. Well, for this part, right, original
over signage.
f of x looked like this, right?
Evacuation plan. I'm pretty sure they're waiting.
So for f inverse of x,
they are not responsible for,
you would subtract 4,
like designing that,
then divide by 3, right? And from here, you would actually subtract 4, subtract 4 from your input,
Okay, I'll look into it again.
and then divide by 3 to get output. Oops. Right, so that's in words.
Mm-hmm.
And using symbols, an equation,
Okay.
f inverse of x would look like whatever your input was, take away 4,
Okay.
and you divide all that by 3. Okay, although this symbol-wise, it looks like the exponent, it's actually read together like this, f inverse. You wouldn't say f of the negative 1. It's read f inverse. So together, over here, right, there's our original function, f of x equals 3x plus 4. Here's our inverse function, f inverse of x equals x minus 4 divided by 3. Okay. All right, so still building on that function machine idea, here's a new person, Kimberly, and she has this new function over here, g of x, and here are the steps that follows, right? We'll jump straight to part A. In our job interview, what equation will Kimberly write for g of x? Well, let's break it down. Here's g of x. Oops, right on the next one. Here's g of x. What do we do first to x? First, she multiplies it by 5. Okay. Subtract 8. And then whatever the result is, they divide that by 2. So following through with order of operations, that's what your equation looks like. For, so this is part A, for x equals 3, g of 3, so here's a reminder on function notation, equals 5 times 3, 15, minus 8, 7, all divided by 2, 3.5. So that's what this function machine would output. On an input of 3, it outputs 3.5, if I did my math correctly. I think so. The new stuff. Kimberly was asked to write the steps for the inverse machine and named it G inverse, right? The inverse of G and its equation. What did she write down? Well, then you would do this stuff in the opposite order, right? Instead of dividing by 2, you would multiply by 2 first. Then, what's the opposite of subtraction? Addition. Then add 8. Lastly, divide, because it's the opposite of multiplication, by 5. Those are the steps. Notice they go in the opposite order as they go here. And then we can write that out as an equation. G inverse of x, and then we'll translate our words into symbols. Equals, multiply by 2, add 8, then divide by 5. We can even go back and check our work, right? So for here, let's make my pen a bit smaller. Oops. So let's check. If we did this correctly, G inverse of 3.5 should give you 3, right? So then we do 3.5 times 2, that's 7, great, plus 8 is 15, divide by 5 equals 3. Nice, we did it correctly. Our old outputs are now our inputs, our old inputs are now our new outputs. It's confusing if you say it, but if you write it out, it's like not so bad. So next part, here's 4 practice problems. You can do so if you have a pen and paper next to you. For the purposes of the video, I'll just do them one at a time. If you're at home, you would pause the video, work on it, then see and follow me as I work through these, okay? Questions from those joining me right now? No? Okay, so if you want a exact procedure for this, often people will think about, okay, to find an inverse, you oh, okay, I'll do that and these practice problems. For this one, we'll follow through what the classwork wants to do, okay? So for n inverse of x, right, first we need to undo this, right, plus 12, and then divide by 4. Right? Because originally our steps was first following through with order operation times 4 subtract 12, right? So now we got to do it in the reverse order, right? And apply the undoing operation, the other operation. So that's why it become add 12 divide by 4. For this one over here for part B, okay, this one the steps for the original, right? Let me write that out. N of x, right? For this one, we have we have j of x. Originally, it was divide by 10, subtract 7.
Yeah.
So then j inverse of x, right, we got to do add 7.
Okay.
All this is going to be multiplied by 10. So that's the same as it writing it this way. Oops.
Okay.
That's the answer there.
Tomorrow?
Okay, it gets a little bit more confusing.
Right?
For p of x originally, right, if we were to write out the steps, what do we do first? Well, we got to follow through with the parentheses, right?
Okay. All right.
Order operations.
Okay. Oh, one more thing.
Add 6.
You have a PDF of
raised to third power,
letter?
right? Or qubit.
Okay. Yeah, just send it to me so I can make those letters. Okay. All right.
Then times 4. Okay. So for C and D, since your process is getting more complicated, it helps to walk through the steps, making sure you undo the proper order of operations. So when we write it out, it becomes easier. Now for P inverse of x, we'll just go through in reverse, right? Start here, go there. So then x is now going to be divided by 4. All this is going to be raised. How do you undo cubing? Like with squaring, there's square root. So this one, you take the cube root, right? And we can represent it like this, right? Or you can write it like this, using our fractional exponents. Okay, that was the second step. And then lastly, we have to add 6 to this thing. Add 6. Add 6. So that's the answer for part C. We found the inverse for this complicated thing. Okay, and I can read it out once. Okay, the original function p of x equals 4 times the quantity x plus 6 cubed. P inverse of x is the cube root of x divided by 4 plus 6. Oh yeah, you're right. Good catch. Thank you. I made a mistake. This one should be minus. Thank you. Good catch. Thank you so much. Minus 6, because here it was add, right? We've got to do the opposite. One more time. P of x, which was originally 4 times the quantity x plus 6 cubed, its inverse is the cube root of x divided by 4, take away 6. Okay, last problem over here. Brown. Okay, originally, t of x, if we were following through with order operations, we got to follow the parentheses first, right? Take away 10 times 15, then lastly, divide by 32. T inverse of x looks like going opposite. So we have our x, we now multiply it by 32, divide it by 15, and then add 10. Okay, the order over there matters. That's part D. We have t, our original function, and now we solve for t inverse. All right, let's say you don't want to write out the steps each time. So here's, oops, I mixed up these slides. Let me see, I have a quick way of fixing it. Copy everything that I wrote. Got it. Undo. Okay, I'm just going to move this over. That. And then zoom out. Drag it down here. Because when I post this, I want to be sure that you have a clean copy so people can still follow along. Looks about right. Kind of. Better? Okay. All right. So then, let's say you want another way to do these, right? Here's 6 more practice problems. If you want a more like a procedure, often you'll see people do it like this. Okay. First off, they don't like function notation, so you can pretend like this one over here. We'll zoom in for part A. It's just the same as y. Don't like the thickness of my pen. So then for this problem, y equals 2x plus 3. Okay, here's another way to find the inverse. Step 1 is flip x and y. So then to solve for the inverse, you do this, plus 3, then 2, solve for y. Then 3, now you have your inverse. So this one, it's using all symbols. Maybe you like this way better. Okay, it gives you the same answer. So now from here, you notice you go minus 3, minus 3. So now you have x minus 3 equals 2y. Divide both sides by 2. Y equals x minus 3 over 2. That's part A. Without like having to write out the steps. This is how I learned it when I had algebra, when I had learned algebra 1. Okay, again, for here, we can rewrite it. G of x is just like y. Maybe I'll do it up here instead. Okay, for part B, y equals x minus 5 over 4. So now we're solving, switch x and y, like this, minus 4. Because the fundamental idea behind finding the inverse is switching your inputs and outputs. That's why this first step works. So now we multiply things by 4. Now we have 4x equals y minus 5. And then we add 5 to both sides. So then y equals 4x plus 5. Okay. I'll leave these other two for you to practice. Maybe you want to do a harder one, and then I'll work through this one. So here, y equals 2 times x plus 1 squared minus 5. You may recognize that's like factored form, or not factored form, vertex form for a quadratic. First one, switch x and y. Then I'll continue over here. Then we solve for y. So our first step is to add 5. Our next step is to divide by 2. We then take the square root of both sides. And then, last step, you take away 1. So y equals square root x plus 5 over 2 plus 1. And you can practice part F, D, and C on your own. So short and sweet lesson on inverses. Idea you will definitely see in Algebra 2 for those taking it next year, and then later in your math classes you'll see this idea again. That's all for today, class. Questions? Oh, you're right, -1. You're right, thank you. This one should be a -1. Thank you. -1. Oops. Go away. Oh, I make this go away. There we go. -1. Thanks. The COVID review will be posted shortly. You can work on this. Maybe I'll throw in a couple inverse problems because they're not so bad. And that's all. Stay healthy. Get a head start on any required classwork. Yes, go ahead. Do what you need to do. This is going to get recorded. You can post. See you later.